This is Ideas Worth Exploring by Mark MacDonald. You're flying through the universe in your spaceship, seeing the sights, having a great time, and all of a sudden you see a black hole. Oh no, it's sucking you in, there's no escape, you're doomed, and it touches you and you're dead. That's how you imagine an encounter with a black hole would look like, right? Well, let me tell you. Well, there's still a lot we don't know about black holes. I can say for certain that that's not it. So let's get started. First of all, what is a black hole? Do they really exist, or are they just fun science fiction things like robots and lasers? Well, first of all, robots and lasers are real, and second of all, black holes are also real. And we even have pictures of them. Wait, but how can you have a picture of something that's basic identity is that no light is able to escape from it? I can explain, but in a minute. First, a black hole is a region of space that has so much gravity that nothing, not even light, can escape. The first inklings that something like a black hole could exist can be traced back to Einstein and his theory of general relativity, is what I thought I was going to say, but it turns out that the idea of a black hole is actually older. But before we go there, we need to take a brief detour back to the days of Isaac Newton. Recall that the physics of how things move was described by Newton in 1687. He said that an object will travel in a straight line until some kind of force acts on it, that things with more mass are harder to move from their straight line path, and that when you apply a force on something, that thing also applies a force of the same strength back on you, which is why your hand hurts after you punch someone in the face. With those three laws I just referenced, we can explain the motion of ordinary objects very well. But to talk about planets and black holes and stuff, we need to look at Newton's other greatest accomplishment, his theory of gravity. You may have heard that he was sitting by an apple tree one day when he saw an apple fall to the ground, and he had a great breakthrough. By the way, you can still see the apple tree today at Woolsthorpe Manor in Lincolnshire, England. It is over 400 years old. Seeing this apple fall caused him to wonder why apples always fall straight to the ground instead of sideways or upward, and this led him to his great discovery. Apples have mass, which is closely related to weight, and he hypothesized that all masses pull on all other masses. Since the Earth has a lot of mass, it pulls on apples and makes them fall to the ground. Since the Sun has a lot of mass, it pulls on planets and makes them fall towards the Sun. That's what an orbit is. The Earth is falling through space towards the Sun all the time, but it's also moving sideways relative to the Sun, so that instead of crashing into the Sun, it misses, and whenever it comes back for another try, it just keeps missing and going in a circle around the Sun instead. For more details, refer to the earlier episode called Newton's Laws Applied to Gumballs in Space. One more Newton thing, and then we can get back to black holes. The idea of escape velocity. Suppose you go outside and fire a gun straight up in the air. But it's not just any gun, it's a magic gun that can shoot a bullet with 10 times more force than the strongest rifle. This gets the bullet traveling so fast that it goes up into space. Of course, gravity slows it down as it travels up, but as it gets farther from the Earth, the force of gravity on it gets smaller and smaller, and if you shot it fast enough, then it will escape the Earth's gravity entirely and go off to infinity and beyond. That's what's called escape velocity, the speed needed to escape to infinity. A planet with a larger mass than Earth will make your bullet need a larger escape velocity because more gravity, and a larger distance from the center of mass will decrease the escape velocity because gravity gets weaker as distance increases. Also, as a side note, rockets we fire off from Earth generally never reach escape velocity because we usually want them to orbit Earth instead of going off to infinity. We do have 5 spacecraft that are on their way out of the solar system, so we can do it, we just usually don't want to. Alright, we can get back to black holes now. The reason I had to review Newton's laws is because in 1783, long before Einstein was ever born, a man named John Mitchell predicted the existence of something that looked an awful lot like a black hole, using only Newton's laws. His reasoning went kind of like this. Stars are fat, as in they have a lot of mass, and that means that the escape velocity from their surface is very large. If you keep on adding more and more mass, eventually you'll get a star that has an escape velocity greater than the speed of light. And based on the science available at the time, he thought this meant that no light could escape such a star, and you would be left with a region of space with tremendous gravity that released no light, which he called a dark star. Sound familiar? Well, we now know that near such a massive star is one of the few places where Newton's laws break down and give you the wrong answer. You have to break out Einstein's general relativity to know what's actually happening. So, let's fast forward 150 years or so to see what Einstein has to tell us. The year is 1915. 10 years ago, Einstein had come out with his theory of special relativity, which says that objects traveling near the speed of light cause time to stretch out and other weird things to happen with space. Now, Einstein had recently published his new theory of general relativity, which says that it's not just really fast speeds that make time stretch out and space act weird, but also large concentrations of mass and energy do the same thing. It's now known that just by standing on the Earth, a very massive object, you experience time about 0.6 nanoseconds slower than you would in the vacuum of space. And time and space get stretched even more closer to the more massive star. Thanks to some work by a man named Carl Schwarzschild, we eventually figured out that if you have enough mass in a small enough space, it causes something weird to happen. At a certain distance from this concentration of mass, the escape velocity is equal to the speed of light. And since nothing goes faster than the speed of light, anything that passes this point of no return, even light, will get stuck inside forever with no possible way to escape. This point of no return is called the event horizon. Kind of like the horizon is how far you can see before mountains or distance blocks your view, the event horizon is the horizon beyond which relativity stops you from being able to see things, because not even light can get out. And this isn't even the good part yet. Inside the event horizon, weird things can happen with time and space. You get pulled towards the center, a point of infinite density called a singularity. You know how in math class you're not supposed to divide by zero or terrible things will happen? Well, a singularity is where the universe decides to divide by zero. And what you get is that the concepts of time and space completely break down. Words like where and when have no meaning, and our current laws of physics have no way to describe it. Because the math predicts such freaky things, it's no wonder that Einstein didn't believe in black holes. But now, 100 years later, we know for a fact that they exist. Sorry, Einstein. Okay, so far we've learned that a black hole sucks everything in, even light, and inside of it, time and space break down. What else? Wait, not so fast. Black holes do not suck. Despite what you've been told since you were a child, despite what every sci-fi show you've ever seen has led you to believe, black holes are not cosmic vacuum cleaners. Here's a fact for you. If you took our sun and replaced it with a black hole of equal mass, we would keep orbiting it as if nothing had happened. Black holes do not suck you in. In fact, it's very hard to fall into a black hole. You can't do it unless you try. There are two reasons for this. The first is that that's just how orbits work. Forget about the black hole for a minute and consider trying to fly into the sun instead. The sun's gravity pulls on the Earth, but we don't say that the sun tries to suck the Earth in. No, the Earth is traveling at a high speed around the sun, and because of that, it orbits the sun instead of falling into the sun. The Earth travels at about 30 kilometers per second around our sun, so to reach the sun, it would need to slow down by that much. By contrast, to leave the solar system, it only needs to speed up by about 12 kilometers per second to reach the escape velocity it would need. So it's more than twice as easy to send Earth flying out of the solar system than it would be to send it crashing into the sun. Supervillains take note. And everything that I've said about the sun also applies to a black hole of equal mass. If you're in a stable orbit around it, you'll stay that way until you purposely decelerate, or you collide with enough things in just the wrong way to slow down. The second reason that a black hole is hard to fall into is that black holes try to push you out. To steal a phrase from Ethan Sagel, black holes are like giant cosmic cookie monsters. A normal meal for a black hole is a cloud of gas or a star that gets too close. And both of these things are really big. A typical gas cloud is many, many times larger than our solar system. A star is not as big, but as it approaches the black hole, it will get spaghettified, or stretched out into little ribbons like spaghetti noodles. Compared to gas and star spaghetti, a typical black hole is tiny. If you replaced our sun with a black hole of equal mass, the event horizon would only be about 4 miles across. A typical black hole is a little larger, but only a little, and an event horizon of slightly more than 10 miles across is a good ballpark. So, as the black hole passes through a gas cloud or near a star, only a small amount actually hits the event horizon. The rest of it will only pass close by and probably start to orbit. Mass moving around a black hole is normally charged, electrons and protons, and as we discussed in the previous episode, accelerating a charged particle releases light. This light carries energy away and lets the matter sink closer to the event horizon. But moving charged particles also do something else. A moving charged particle creates a magnetic field, and a bunch of them moving together can make a very strong magnetic field. And what this all adds up to is that the magnetic field makes more than 90% of the infalling matter get spit back out at high speeds in jets. In fact, it may be as much as 99%. That's why I said that a black hole is like a giant cosmic cookie monster. Very little matter actually reaches the event horizon. Most of it just gets broken up and then spat back out. All of this is not to say that it's safe to approach a black hole. Oh no, far from it. But it's not the black hole sucking you in that you have to worry about. It's the matter orbiting the black hole, gas clouds and star spaghetti traveling near the speed of light that could rip a hole in your ship like a bullet through wet tissue paper that you should worry about. A black hole is not an inescapable vacuum so much as a hive of murder hornets ready to punch you full of holes. Of course, not all black holes have stuff orbiting them, so if you find an unarmed black hole, then you really don't have anything to worry about. At least if it's a small one. If you think you're safe near a large black hole, then you clearly don't understand the gravity of the situation. For a supermassive black hole, once you get close enough, the difference in gravity between the side of you closest to the black hole and the side furthest away will be large enough to yank you apart. Stars aren't the only things that get spaghettified. You can do it too. For a black hole the mass of our sun, you'd actually have to pass the event horizon for gravity to be strong enough to spaghettify you. But for a supermassive black hole, it could happen much farther away. As a side note, you actually don't even need a black hole to get spaghettified. There's a different type of very massive body called a neutron star that'll do it too, but that's a whole nother story. Alright, we've had bits and pieces of it, but now we're going to talk about what a black hole looks like and the different parts it's made of. Let's start in the middle and work our way out. As mentioned, the center of a black hole, where all the mass is confined to a single point, is called the singularity. But that only happens if the black hole isn't spinning. If the black hole is rotating, which it usually is, then instead of a single point, you'll have a ring. Then it's called a ringularity. Moving out from there, you get to the event horizon, the point of no return I mentioned. If you cross the event horizon, you might not even realize it. There's nothing there to tell you this is the point of no return. But once you go over, there's no coming back. Farther out from the event horizon is the orbiting cloud of junk, called the accretion cloud. As matter orbits, particles collide with each other, and some of them gain enough energy to escape to infinity, while others lose energy and move closer to the black hole. The accretion cloud is made of particles moving near the speed of light, so they could rip apart your spaceship as easy as pie. The moving particles also release a lot of energy as light, which is why a black hole is visible and capable of being photographed. Sometimes the matter in the accretion cloud is released in jets along the axis of rotation of the black hole. Sometimes, looking through a telescope, we see spots in the sky light up randomly. That is sometimes a jet from a black hole, shining brighter than the entire rest of the galaxy it's sitting in. And finally, between the event horizon and the accretion cloud is a region of nothing. It's not past the point of no return. If your spaceship is fast enough, then you can still accelerate out of it. But past this point, there are no stable orbits. This isn't a thing that happens with Newton's laws. You need Einstein to explain it. But in this region, the black hole actually does end up sucking you in. Yes, I lied to you. black holes do suck, but only a little. This region is very small. If our sun were compressed into a black hole, then to get to this region that sucks you in, you'd have to go quite a ways past what is currently the surface of the sun. So don't worry about it. You'll die from the accretion cloud long before you even get there. Okay, the hard proof of black holes' existence. We have pictures. In 2019, a single photo was released that showed the combined efforts of 13 of the world's greatest radio telescopes. No single telescope was enough. They had to combine signals from all 13 to get the information they needed. And they couldn't combine the signals in real time. In fact, there was so much information to work with that they couldn't even send it over the internet. They ended up storing the information on disk drives and physically carrying those disk drives to a central location to be analyzed. The South Pole telescope was in the middle of winter, so it had to wait several months to be able to ship their data. But they did it. We currently have images of 2 different black holes. One of them is in a far-off galaxy, but the other is a supermassive black hole in the center of the Milky Way. It's called Sagittarius A star, and it's 4.6 million times more massive than the Sun. The image looks kind of like a glowing donut. That's the accretion cloud you see, the gas and stars that the black hole is devouring, letting out their last calls of help before they're torn apart by the lump of blackness in the center. Moving on. I've mentioned supermassive black holes several times now. What exactly does that mean? Well, they're like normal black holes, except instead of just being massive, they're supermassive. Okay, that probably wasn't very helpful. Let me back up. When I say normal black hole, I'm referring to what's typically called a stellar mass black hole, or a black hole that has a mass only a couple times larger than our sun. These typically form when a large star dies explosively. When a large star uses up all its fuel, the pressure inside drops enough that gravity takes over and causes the star to collapse in on itself violently. This creates a supernova, the biggest explosion humans have ever seen. And if the star started out the right size, then the mass remaining in the center will have been compressed enough to collapse into a single point and form a black hole. Stellar mass black holes are formed by stars collapsing, and they usually end up between 3 and 10 times more massive than our sun. But there's also another type of black hole that we've observed out in space. Supermassive black holes are black holes between a couple million and a couple billion times more massive than the sun. And this is very weird. We've seen black holes 10 times and 1,000,000 times heavier than the sun, but almost none in between. Intermediate mass black holes are very rare. So how do these monoliths that are many times larger than the human mind is capable of comprehending come to be? Do they grow from stellar mass black holes merging together? Or did they start as primordial black holes created just moments after the Big Bang? Yeah, we don't actually know. There are problems with both theories. But there's a supermassive hole in the center of most galaxies that we've been able to look at, so that's kind of neat. There's one more type of black hole I want to mention: micro black holes. This concept was introduced by Stephen Hawking, which is a name that will come up quite a bit if you start a serious study of black holes. The idea is that any amount of mass compressed down small enough would form a black hole. If you compressed Earth enough, then it would become a black hole. But you'd have to compress it down to 1.77 centimeters, or less than an inch. According to vanilla general relativity, you would become a black hole if you were compressed down small enough, but you would have to be compressed to 10 to the negative 25th meters, which is 1,000,000 billion times smaller than an atom. Also, when you add in quantum stuff, you get a new theory that says that the minimum mass a black hole can have is 10 to the 16th kilograms. So, if for some reason instead of being buried or cremated, you've always dreamed of having your body turned into a miniature black hole after you're dead, I'm afraid you're out of luck. Also, we still haven't ever seen any evidence that micro black holes exist in nature. It might just be something that's conceptually possible but impossible to realize. So, even after all this, you probably have one more question. What would happen if you fell into a black hole? Let's put everything together and go over it step by step. First of all, as I said before, it is very hard to fall into a black hole by accident, so assume you're purposely steering your ship into it because it is the deepest desire of your heart to die in a black hole. Okay, sure. Assume you make it past the murder hornet defense system that's the accretion cloud without having your ship torn to bits. Assume that it's a small enough black hole that you're able to approach it without getting spaghettified. So you approach the event horizon, where space-time is bent enough that Newton's laws no longer tell you how things move, and you have to consider Einstein's relativity. In the episode about relativity, we talked about how time passes differently when you're moving really fast. Well, the same thing happens near a black hole. As you get close, time passes faster for you than it would for someone watching you from far away. It's like in the movie Interstellar. 1 hour here is 7 years back on Earth. That worked in Interstellar because they were near a supermassive black hole, with about 100 million times the mass of our sun, according to the creators of the movie. Near a stellar mass black hole, time will also slow down, but only if you get close enough that you're almost touching the event horizon. As you get closer, the time difference grows larger. To a distant observer, you appear to slow down as you approach the black hole and stop when you reach the event horizon, frozen there for eternity. But you also won't be visible for long. As you get close to the event horizon, less and less light gets out to reach the observer, so they will see you grow fainter and fainter and then disappear completely. But to you, passing beyond the event horizon, time will appear as if it's passing normally. In fact, you might not even notice it as you pass the point of no return. Once you pass the event horizon, there is no way to ever tell anyone on the outside what you see in there. The gravity is too strong for any signal to ever escape. There is no such thing as an orbit anymore. All possible trajectories lead you to becoming one with the singularity in the center of the black hole. Very zen. There is one exception. Inside a charged, rotating, ultramassive black hole, it might be possible to find a stable orbit, maybe even one that a planet could use, inside a black hole. So yes, there's a chance that some advanced future alien civilization could live on a planet inside a black hole. But no matter how advanced they are, they still won't ever be able to escape. Well, that's it. Why didn't the black hole finish its meal? Because it was a light eater. Why do all planets want to date black holes? Because they're so attractive. In summary, black holes are concentrations of mass large enough and with enough gravity that not even light can get out. When you're far enough away, they behave like stars of equal mass, and you orbit them like Newton says you would. But when you get too close, you get things like the event horizon, a point of no return where time slows down, and the accretion cloud, a glowing cloud of gas moving near the speed of light that will tear your spaceship apart if you try to get too close. The nice thing about a glowing accretion cloud is that we can see it. We actually have photos of 2 black holes, and one of them is a supermassive black hole in the middle of our own galaxy. There are also probably lots more black holes in our galaxy, but they're very hard to see, so we might never know exactly how many there are. I hope that if you remember anything, it's that you shouldn't be worried about being sucked into a black hole. No, black holes can kill you in many ways, but being sucked in is one of the least likely. So don't worry about it. I hope you enjoyed this episode. Come back next time for more science and puns. Peace. This has been Ideas Worth Exploring by Mark McDonald.